All right, continuing to review for exam 2 here in lecture B. Let's look at this actuarial example. I posted this morning on Moodle. We're going to be finding a present value, an actuarial present value. Actually, I gave you the formula for that. But as an actuarial present value, that means it's a random variable. And that means we want to know things about it that we want to know about random variables, continuous random variables. We want to know their PDF, their CDF, their mean and their median is the main things we focused on. So I've got the background here. I'm telling you a lot of things already. It's a lot to read. I think on your exam, I will give you a similar question, except perhaps give you even more information. You still kind of have to wade through the reading. How do you get a quick idea of what's going on so that you can get your mind around it? T is the lifetime random variable. It's how long something lasts. How long a person lasts until they die, how long a washing machine lasts until it breaks, etc. I'm assuming it's got a uniform distribution. F of t is 1/10 for t between 0 and 10. That's its PDF, its density function, probability density function. Integrating that to get a particular antiderivative that starts at the origin and heads up to 1 when t is 10 gives you the CDF, and there's the formula. Notice the domain too. Integrate the PDF to get the CDF. Here's my actuarial present value. A new random variable, z, is $1,000 times e to the negative 0.04 times t. What does that represent? Some future payment, like when the washing machine breaks, $1,000 at some unknown time. Capital T is a random variable, how long a given customer's washing machine will last. You don't know how long that's going to be, they don't know how long it's going to be, but you can model it with probability. It's going to, according to this model, die sometime between 0 and 10 years. So this quantity is going to be somewhere between 1,000 e to the 0, which is 1,000, at the high end, to, if it dies at 10 years, this is 1,000 e to the negative 0.4. Negative 0.04 times 10. That's as small as that can be. So z is going to be somewhere between 1,000 e to the negative 0.4, which is this, and 1,000. That's going to be the domain for the PDF and CDF of z. Now we want to find that PDF and CDF, though in these kinds of situations, I'm just telling you for the future in case you encounter this in the future, it's easiest to find the CDF first, then the PDF. Usually we do it the other way around. Usually we write the PDF first, right? Based on some data and some modeling and seeing what kind of distribution it has, maybe uniform, maybe exponential, maybe normal. We write down what the PDF is and figure out the CDF by integrating. But when you got this kind of setup, it's easier to figure out the CDF first. I'm calling the CDF capital G for this random variable z. CDFs are always this kind of probability. They are always the probability that a random variable denoted by a capital letter is less than or equal to some particular value of that variable, denoted by a lowercase letter. Ultimately, the lowercase letter becomes the variable for this function, but the capital letter is the random variable. What is this kind of probability? That's always what CDFs are. Well, what is z? Z is that. I replace the capital Z with that. And your initial goal here is to do some algebra to try to rewrite this probability in a way that allows you to use capital F, the formula for the CDF of capital T. We want to use that somehow. By doing the algebra, you can get it to here. And in part A of this made-up problem, I've never asked an exam question like this before, so I just made this up this morning. I say show algebra steps that confirm that you can get from here to here. So it's a matter of carrying the P along and essentially working with what's inside the parentheses there and just solving the inequality for capital T. show those steps. Divide both sides by 1,000 first, to get rid of that 1,000 there. Then you'd have e to the negative 0.04 capital T still on one side. Get rid of the e by taking the natural log of both sides. Natural log is an increasing function, so the inequality stays the same direction. After doing that, you're going to get this on one side by itself. You want to isolate capital T like that. You got to divide both sides by negative 0.04, which is the same as multiplying by negative 25. That's a negative quantity. The inequality switches direction from less than or equal to greater than or equal to. But just as if the chance of rain tomorrow is 20%, there's an 80% chance of no rain tomorrow, this probability is the same as 1 minus this probability. Oops, I think I got the inequalities there the wrong direction. I mean, this is still true. But I meant to have a greater than or equal to there and a less than or equal to there. I'll switch that around before I repost it. It's still true either way. You can still use it to solve for what you want. You might wonder, should this be a strict less than instead of a less than or equal to? With continuous random variables like this, it's okay to put less than or equal to. Don't worry about it. This kind of probability with a less than or equal to there is what I should have put, is related to the CDF of capital T. It does equal, this thing here, this entire thing does equal capital F of T. Because it is the CDF. It's probability that capital T is less than or equal to some little t. It's just like all CDFs, like I mentioned back here, are of that form. So this expression can get replaced with capital F of T in this setup, which means that this thing equals 1 minus this thing. Replace the little t with this entire thing, because this is playing the role of little t. Here and here. So then, I mean, I'm not just telling you all this, I'm even telling you what it simplifies to, this, and you can also simplify to that. Then I'm saying find little g, the PDF. Well, if you integrate the PDF to get the CDF, I guess that means you got to differentiate the CDF to get the PDF. And yeah, that's what you do. Differentiate. G, little g of z is capital G prime. And in this last form, it's easiest to differentiate. Those are constants, they differentiate to 0. This differentiates to 5 over 2 is equal. That's the PDF. I'm telling you its domain as well. So the graph would look about like this. This would be 1,000 here. And actually, I think 1,000 e to the negative 2/5 is 600 something, if I recall correctly. e to the negative 2/5. And you should, I don't ask you to do this, but I would recommend doing it. You should check that the integral of this over that domain is 1. This is a PDF. Part C, find this probability. You integrate PDFs to find probabilities, or, more simply in this problem, do a difference from the CDF. You've already got the CDF. Antiderivative, capital G. Just do a subtraction. This is just going to be capital G of 900 minus capital G of 800. Which is the same as the integral of little g from 800 to 900. And then finally the median is where capital G equals 1/2. We gotta solve that equation for little z. Oh, and I forgot the mean. That's the median. The mean, you got to integrate z times little g over the domain, which is again 1,000 e to the negative 2/5 to 1,000. That integral for this kind of problem is actually going to be pretty easy. Think about it here. Little g is this. Multiply that by z. The z's will cancel. You'll be integrating a constant to find the mean. Okay, I'll go ahead and tell you your actuarial problem will be similar to this with changed numbers. And I may even skip part A and just go right to parts B, C, and D. How do you figure out little g? How do you figure out a probability? Figure out the mean and figure out the median. But then there's this background stuff to read, which is maybe the hardest thing is just how long it is to all state and you're trying to get your mind around it. But if you practice this and practice it maybe even a couple times, then you can probably go faster during the test. Any questions on that?
Can you explain like the relationship between capital Z, capital G of Z, and little g of Z? Like how do you
Say again, between what and what?
Between capital Z, capital G of Z, and little g of Z?
Yeah. Capital Z is a random variable, a quantity whose value is undetermined. It's going to be different for different people, different for different washing machines. We can model how random variables behave over many customers and many washing machines through this PDF and CDF idea. Capital G is the CDF for Z, little g is the PDF. Usually when you're doing modeling, you think about the PDF first. You maybe have some data, and you make a histogram or bar chart showing how the data are distributed. Is it approximately uniform, for example, with how long something lasts? Or is it exponential, or is it normal? You use your data analysis to try to figure out the PDF first, and then integrate them to find the CDF and to find probabilities. In this kind of stuff, it's easier to take the known quantity, the known distribution that you're assuming works for t, and using this equation to figure out corresponding things for z, and figuring out the CDF first instead of the PDF. It's the opposite direction, just because it works out easier this way, is the idea. So the PDFs and CDFs are really both useful depending on the situation. Does that help make the connection? You sort of, you need to rethink about these things kind of over and over. And when you do, it does start to become more clear, right? When you do think about these things over and over again. Try this problem over and over again and make graphs and think about it. And you can even take my code and do the simulations if you want. You just run my code if you make adjustments to the formulas. It does come to life with simulation. That's why I do the simulation. It makes it seem more real, I think. The probability is really modeling stuff, and that modeling can be simulated. And the simulations are also sometimes necessary if formulas just are too complicated. Sometimes formulas are too complicated to use very well, and so you want simulations instead in those situations. Okay. Then, sequences in series, chapters 9 and 10. There's a lot of stuff in there, huh? What do we have here? 20 minutes or so? Maybe with that I should start at the end and work backwards. Start with the Fourier series so we can make sure we get that in. And work backwards. And maybe we should continue focusing on these practice problems. So let's go up to the Fourier series 1. Right there. So our function is this. And by the way, in case it wasn't clear, we assume the function does go on periodically like this forever. So when you get to pi, it comes back down to -1 until you get to, what would it be? 5 pi over 3, it looks like. Where it would be back up to 0 until you get to 7 pi over 3. Then it would go up to 1 until you get to 2 pi. That's the way it looks like. And this function would continue in both directions forever in a periodic way. It's not exactly an odd function because of the endpoint issues that go on. For example, in this graph, we do not include this endpoint, but we do include this endpoint. Not this one, but we do include that one. And because of that, it's not technically an exactly odd function, but it's basically odd. And with respect to integration, it would be odd in the sense that integrating the function itself from negative pi to pi would result in 0. And also, if you put a 1 over 2 pi in here for the a0, you're going to get 0. The AKs in general are going to be 1 over pi times the integral from negative pi to pi of f of x times cosine of kx. And even though an odd number times an even number is an even number, it's not that way for functions. An odd function times an even function is an odd function. This integral ends up being 0 as well. Question?
For a-naught, like on the test, are we gonna have to show me work for that, or can I just 0?
Yeah, I'm in fact just telling you with this problem that it's 0. There. And probably I give you a similar problem where something like that might happen.
Will you tell us when it's an odd function, or how will we?
Well, yeah, I mean, I did say it's basically odd here. Again, it's not exactly odd, but basically odd with respect to integrals. And I did tell that this was an old problem that I put in an old exam, and so I did tell them that. I probably would tell you something similar to how to do. Ultimately, I'm just having them do one integral to find b1. bk in general is 1 over pi times the integral from negative pi to pi of f of x times sine of kx. Since f of x is basically odd with respect to integration, times another odd, here's another funny thing, an odd function times an odd function is an even function, even though an odd number times an odd number is an odd number. And you could try this kind of stuff with basic examples, you know. X cubed is an odd function, x squared is an even function, their product is an odd function. X cubed is an odd function, x to the 5th is an odd function, their product is an even function. So you're adding the exponents. The multiplications essentially work more like adding does. When you add an odd and an even number, you get an odd number. Okay? With these examples, you can see why that happens. As an odd times an odd, you get an even function here, and therefore you can do the integral more simply by doing the integral from 0 to pi and doubling it. So this is a work-saving thing here, by the way, what I'm showing you, and could come up on your exam that you might want to save work this way. It's always easier to integrate starting at 0, or often easier. What did they have to do? They had to calculate b1 here. So that's 2 over pi times the integral from 0 to pi of f of x sine of x. The k is 1. That's not as hard as it looks. F of x is 0 between 0 and pi over 3. So you can ignore that piece. And it's 1 otherwise. So this integral simplifies to 2 over pi times the integral from pi over 3 to pi of just sine of x. Because f of x is 0 between 0 and pi over 3. So I can start my integral at pi over 3. It's a 1 between pi over 3 and pi. 1 times sine of x is sine of x. And now that integral is pretty easy. Negative 2 over pi cosine of x. Evaluate from pi over 3 to pi. Negative 2 over pi. Cosine of pi is negative 1. Cosine of pi over 3 is 60 degrees. That is 1/2. So we get negative 2 over pi times negative 3/2. This becomes positive 3 over pi, it looks like. That should be the answer, unless I've made a mistake. I think we're okay. Looks like b1 is 3 over pi. I'm telling them the total energy of this function is 4/3. What do I mean by energy? This actually does relate to physics, by the way. If you had a sound wave that had this kind of graph in appropriate units, the 4/3 really would be the energy produced by the sound wave, maybe per unit time or something. You can confirm the energy in this case. You integrate f of x squared from negative pi to pi. Now I forget to divide by pi or 2 pi. I gotta look up these formulas sometimes myself. For the energy of a function, you divide by pi. You could check this on your own. Might be a good exercise to see that with this function, this integral equals 4/3. The energy corresponding to this coefficient is its square. B1 squared, I'm just telling you, 9 over pi squared is the energy corresponding to that coefficient. It's in the Fourier analysis, in that power spectrum idea, it's the height of the line above the first harmonic, essentially. A1 is 0. A1 and B1 would both contribute energy to the first harmonic, to the first fundamental frequency, or different words you can use. And the energy corresponding to that would be, in this case, B1 squared. In general, if you had a non-zero A1, it would be A1 squared plus B1 squared would be the energy corresponding to the first harmonic. You'll see these formulas in the book. But A1 is 0 here. What fraction of the total energy is that? Just take the ratio, 9 over pi squared divided by 4/3, which is the same as 9 over pi squared times 3/4. 27 over 4 pi squared is the fraction of the energy from the first harmonic. That should be a number less than 1. Hopefully it is. 27 over, well, that's not in input mode. Come on. Input mode. (27 over 4 pi squared). I think I got the answer 68% when I did this. So this should be around 0.68. Yeah, 0.6839. So 68% of the energy is coming from sort of this fundamental harmonic, the lowest frequency contribution, essentially. And there are more energies coming from higher harmonics that have a higher frequency. But that's the percent of the energy inherent in the sound wave that's coming from the first harmonic. Maybe that would be the most dominant thing you would hear. The most dominant, related to the most dominant frequency you would hear if we amped up the frequency of this thing overall to being more into the audible range. It's not in an audible range right now. The frequency is too low. Question?
If there was an A sub 0, would that be the fundamental harmonic then? If you wanted
I don't know what to call that. That's sort of like background noise or something, if you have an A sub 0. Again, I'm not an expert on physics or sound waves. You kind of sort of think the A0 as being a 0th harmonic, and I would sort of think of it as like background noise, sort of an ambient rumble or something.
So if it was there, you would still use the A sub 1 and the B sub 1 term if those were terms?
Yeah, this would still be the energy of the first harmonic, I think. This is all described in page 570. You know, we're not worrying too much about the exact natures of the physics and how you really use these kinds of things in physics. That's what physics classes are for. We're trying to get the basic idea and at least do some calculations. Basic idea. All right, moving backwards through chapter 10. Got Taylor series in general and tricks for calculation. Let's see, so a bunch of problems here. Problems 1 through 8 have a bunch of stuff related to series. So does 9 and 10. And so does a 14, it looks like. And 15 with differential equations in there. Oh, let's see. I think we're going to skip the differential equations for the moment. I don't know if we'll have time. Probably not. Wait, I've got a bunch of examples here. You've got your note card. You can use them in the exam front and back. Whatever you feel like is most necessary for you. But again, you really should work at trying to remember these things. For example, the series for sine of x. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. It goes plus minus, and you'll have all odd powers and odd numbers being factorial. That's a word. Replace all those x's with x squared, you'll get, that doesn't work either. X squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial, etc. Simplify and multiply the x through, you're going to get x cubed minus, that'll be an x to the 6th times x is x to the 7th over 3 factorial plus x to the 11th over 5 factorial, etc. So you could calculate something like that pretty quickly if you got these things memorized, and you don't have to just be searching through your note card. The note card's there just for security, help lessen the anxiety, and you only look at it if you really, really need it. And also to remember, this converges for all x. This is for all x. And the series for the sine function does converge to the sine function. We never proved that, but we're trusting that. Something like this is that's like a geometric series sum. A over 1 minus r, where a is 3 and r is negative 9x squared. So it's a plus a times r plus a times r squared plus a times r cubed, etc. I do want you to put the plus dots in there for full credit. Glad I remembered to say that. I do want you, even though it says find the first 3 non-zero terms, so in the directions here it's not explicitly stated. I might try to explicitly state it. I do want you to put the plus dots to emphasize you know it's the infinite series that equals the original function, not a finite Taylor polynomial. And then you can simplify this, and you should simplify it. Even if I don't explicitly ask it, you should simplify it. We can simplify to like this here. And those are the first 3 non-zero terms plus ... And you know the series for geometric series converges when the common ratio is less than 1 in absolute value. So the absolute value of negative 9x squared must be less than 1, which means absolute value of x squared must be less than 9. Or excuse me, 1/9, sorry. And then take the square root to absolute value of x must be less than 1/3 for this example A. The interval of convergence is from negative 1/3 to positive 1/3. The radius of convergence is positive 1/3. You should be able to calculate that radius of convergence with the ratio test at all, although I don't have time to do the example calculation. So if you're rusty on that, practice some ratio test calculations. In part B here, I said finding for arctangent of 3x. Note the derivative of arctangent of 3x is the answer for A, or is question A. So if we integrate the answer for A, we should get the series for arctangent of 3x. Got that? Since the derivative of arctangent of 3x equals that, which is that, if we integrate this, we should get the series for arctangent of 3x. Plus c, the c can be 0 since arctangent of 0 is 0. Sometimes you have to differentiate series, or it's the quickest way to get it at least, like for this one. That function is not only the square of 1 over 1 minus x, so you could square the series for 1 over 1 minus x, but you can also just differentiate the series for 1 minus 1x. 1 over 1 minus x. This note here, I sort of emphasize that you could find the answers 2 ways. You only have to pick one of them. You don't have to do both ways, though you might want to check. Practice. This one involves the binomial series with p equal to 1/2. Anything else? So and that kind of binomial subseries will converge when this is true. To get the one for natural log of 1 plus 2x, you want to integrate that one, series for this one. And this one is sum of a geometric series. Do this.
I have a question on vector B. When you were saying that you would just have to integrate the answer for A, would you plug in 3x for all of the x's that you found? Like,
No, just integrate it as is.
okay.
You know what, you should be able to do it with the other formula involving the derivatives. You should know this formula and be able to use it if I ask you to use it. Thinking back into chapter 9, there are a bunch of other tests. I mean, I mentioned the ratio test. There's the alternating series test. There's the comparison test, the limit comparison test. Lots of tests. There's the most fundamentally, the divergence test. Do the terms you're adding go to 0? If they don't, the series diverges. If they do, the series might converge and might diverge. You have to try some other method. P series, converge when p is bigger than 1 and diverge when p is less than or equal to 1. When it equals 1, it's the harmonic series. You can prove p series converge or diverge based on p by the integral test. Doing improper integrals and seeing if those converge or diverge. And most fundamentally in chapter 9, to know that a series converges or diverges completely based on the sequence of partial sums. And we looked at examples involving geometric series, because you can find a nice formula for the sum of a geometric series I forgot to mention for the finite case. This has a nice formula. It equals a times 1 minus r to the n plus 1 over 1 minus r to 1 minus r. The power there is always the number of terms. And since we're starting with r to the 0 power, there's n plus 1 terms here. That's a partial sum for this, the corresponding infinite series. We also looked at examples where you had to do some partial fractions to help you simplify the formula for the partial sum. Not sure if that's going to show up on the test or not. I actually have not started writing the test. Okay, I'm about to this afternoon or tonight. I will get it done in time. There's a few people who need to take it early. I may take some of these problems on the practice sheet and just modify some numbers. I might do that. So working on this problem will be good. All right, have a good day.